All right, so we're here talking about, first of all, some homework on decision theory, and then we'll start taking a look at networks. So let's start by looking at the homework on decision theory, and you could do this two ways, either in Mathematica or in R. This is one where I think it's a little easier in Mathematica, so let me go through this first.
Are you ready for your students? Because I'm keeping them
Ah,
out.
that's where they are.
You asked me to keep them out. So
Yes,
I'm keeping
bring them in.
out.
Oh.
Okay.
Well,
Sorry.
so we had all this theorizing as to why they weren't here, but really the answer was my secretary. You guys got in before she...
She caught us. Yes.
We hadn't created problems.
Welcome back. Okay, well, while you were waiting, I went through exactly what would be on the final, but I'm not going to repeat that, and we'll just keep going. Today's lesson plan is to go through problem set 11, the answers, and then to move on to networks. As I was mentioning to those who snuck in before and breached my security system, I have changed Monday's class. Monday's class will be a review session. So a review session works best when you send me things that you don't understand and I have an opportunity to think through an answer. So while you're carving up that turkey and watching a Detroit's Lion game or something, think about what questions you have and email them to me, and I'll do my best to answer them. The other benefit is there was a problem set I was going to hand out that day. That has been X'd. So no more problem set for that day, and I'll just count the final a little more than I would have otherwise, and hope that doesn't disturb anyone. All right, so why don't we start on the problem set, and I want to do it in Mathematica first, and then we'll do it in R. And at the moment, I have my R answer, one of them does not reconcile with my Mathematica answer, and so there's actually a mystery lurking here which you can help me solve, which is where is the mistake? Okay, so your job is to figure out what I have typed wrong. All right, so you remember our setup here is...
I'm making the blowing it up.
Better?
Yes, thank you.
Okay. Our setup is we've got plaintiff Paula, she's suing for breach of contract. Trial's over, she's waiting for the jury to come back, and there's a 40% chance she's going to lose, or that's what she thinks, and a 50% chance she'll recover $10,000 and a 10% chance she'll recover $64,000. And good old Paula, being the person that she is, has a square root utility function, and so we're interested in the certainty equivalent wealth of Paula's lawsuit as she perceives it, and also to see whether that certainty equivalent wealth is greater than or less than the $7,500 the defendant just offered to settle the lawsuit. So Paula's got to figure out whether she wants to settle it. Okay, so this is a fairly straightforward problem. We're going to compute her expected utility, and we're going to do that by mapping her utility function over the range of outcomes. And then we're going to take the expectation of that. I could have done this in many ways. I took the cheap, simple way out of simply dot producting the probability vector with the expected utility, and then I squared the result took the inverse of the utility function to get back to where I started. Does anyone have questions on what I did there? Just as an alternate method, here's another way that one could do it. One could start with an empirical distribution in which the probabilities were 0.4, 0.5, and 0.1, and the outcomes were the trial outcomes, the corresponding trial outcomes. Okay? We could then transform that distribution according to her utility function. So we're going to take the square root of x, assuming that x is distributed according to this. We could then take the mean of the transformed distribution, and that gives us, or I can simply take, I can take the expectation of y, could you, yeah, thank you. assuming that y is distributed according to this transform distribution. And that will get me something if I put in a comma. I want to take the expectation of y, assuming that y is distributed according to this transform distribution. When I get that, I get 75.29. That's sort of a meaningless number, but that's our expected utility. And to get back to her certainty equivalent, well, I am going to do that final operation of squaring it. And so I get it this way. So either way you do it, this is sort of the fancy right way, and this is obviously takes a lot less typing. All right, and one of the reasons I say it's the right way is because you can sort of immediately move into figuring out things like the spectral measure. So we learn here that our friend Paula uses spectral measures, and her weighting function is the PDF of a beta distribution with parameters 1 and 2. All right, so the idea here, remember, is that we are weighting the worst outcomes in disproportion to their probability, weighting them more heavily, weighting the good outcomes in disproportion to their probability, but weighting them lower than their actual probability. So it's a weighted average of the outcomes, but one in which pessimism is emphasized. All right? And so the way we're going to do that is we're going to take our same empirical distribution of outcomes. We're going to calculate the quantile function, which you remember is simply the inverse of the cumulative distribution function, and the 90th quantile of a GPA is 3.5, and all these things that help you remember what this sort of weird function is. The beta distribution simply serves as a way of weighting the outcomes, and when we run this, we get 4140. And so either way, the defendant settlement offer of $7,500 is actually a decent settlement offer. And maybe Paula could try and, negotiate to boost it up. But at least it would not be irrational for Paula to accept that settlement offer rather than going to trial, assuming that this is how Paula regards risk. Okay? So, problem 3 asks us to take a look at a structured settlement, which you might encounter in the real world. And the structure is that it's basically, I'll give you more money, $10,000, but I'm going to spread it out over 4 years. Basically, I'm going to give you an annuity of 4 years. And the only catch is that you have some doubts that the defendant is actually going to pay this you don't need to see right now, the final installments. So there are sort of two parts of this. One is to figure out what the value is of this annuity, assuming that it is paid for Y years. And then the other is to figure out what the probability is that each of those years will materialize. Okay? So let's first of all do, I think, the easier part, which is to figure out what is the value to the plaintiff of this settlement. And we're going to hearken back to our time value command. And basically what the defendant is offering is an annuity due, in which the payment is made at the beginning of the period, and it's going to be made for Y years, where Y is anywhere from 1 to 4. We're going to discount it at Paula's rate of discount 0.04 and bring everything, the apples to apples, back to time 0. So that's what we're going to transform, if that makes sense. And now the only question is, what distribution are we transforming? And the way you might think about this is to look at the hazards that, the hazard of failure. So the hazard of failure in the first period is 20%. There's a 20% chance that that second payment is not going to be made. The hazard of the next payment is 25%. That is, there's a 20% chance that we're going to fail, but our denominator is 80%. We're only starting with 0.8, and so the hazard is 0.25. The hazard the next period, we start at 60, we end at 40, so we've lost 20, we've lost a third, so the hazard is 1/3. And so what you can then do is to use that to calculate the differences here. Okay? And maybe this is overly elaborate. Is it overly elaborate? Maybe. And I don't know why this UCC thing keeps popping up. But when you do this, what you find is that the probability of only the first payment being made is 0.2, only the second payment being made is 0.2, only the third payment being made is 0.2, and the fourth payment is 0.4. And that would be for 1, 2, 3, or 4 years. All right, so we can calculate what is the quantile with respect to Q of this now transformed distribution, and we get this funky thing. And we can then take the expectation of that, weighting it again according to our beta distribution, 1, 2. And when we do that, if my mouse works, we get 52.26. And so that's how much the settlement is worth. It's actually not as good a settlement offer as the $7,500, both because there's a time discounting element, but more significantly because it's not clear the defendant is actually going to pay all of the money. Okay? Problem 4 asks us to look at the things from Dennis's perspective. We're told, and this is never the case in the real world, that the defendant actually secretly shares the same estimate of likely outcomes of the jury verdict as Paula does. In real world, you end up believing your own nonsense, and usually litigants have an overly optimistic guess as to how they're going to do at trial. So the question is, what's the most amount of money Dennis should offer to settle the lawsuit? And Dennis uses this thing where he has an order distribution where if 2 outcomes occur, Dennis thinks it's going to be the worst thing. Okay? So there are a couple of ways we can do this in Mathematica. One is to actually construct an order distribution. And so I've done that for Dennis, putting negatives here for his outcomes rather than positives, and saying I want the worst outcome. And then what I can simply do is to take the mean of that order distribution. And that is a way of simulating a risk aversion. Okay? The other way to do it is, if you remembered, I told you that taking an order distribution is actually the same thing as spectral measures with a beta distribution, where this is the outcome and this is the number of rolls. So we can simply use our spectral measure idea, and we don't have to construct an order distribution, and we get the same answer. Okay? So those are 2 ways that one might have handled this problem. The other way would be to do a simulation. And actually, let's just do a simulation and see how good our simulation would be. Okay, so there's our thing. Let's take a random variate of that, and we'll take 10,000 random variates. Okay, there they all are. How are we going to partition them into groups of 2 and then take the worst? Well, here's how I do it. I would say, let's partition this into groups of 2 with offset 1. That is, I'll take the first 2, then I'll take the second and the third, then I'll take the third and the fourth and the fifth, the fifth and the sixth. And since these are independent draws, I'm getting a lot of samples that way. So we do that. And here are our pairs. Now what I want to do is take the worst of all of these. So I'll take the minimum and map that onto this. So those are the worst cases of each of my draws, and then we'll just take the mean value of this list, and if all goes well, it's exactly 61,574,000. Thank you, Wolfram. And so in this, it came out to negative 18,388. So not a bad estimate, and probably if I did 100,000 of these, we'd start to see convergence. Okay? Isn't it amazing you can just do that in draws? I think it's amazing. All right, problem 5 is where there's a little bit of conflict with Mathematica and R, and I suspect strongly that the problem has nothing to do with Mathematica or R. The problem is user error. So your job here is to spot where Chandler has gone wrong, and of course you don't know if it's in this side, the R side, or both. So, all right, we're here. What's our problem? Our problem is we're a mediator. Everyone agrees the damages are $100,000. We're about to go to summary judgment, and here's what the plaintiff thinks. The plaintiff thinks there's a 50% chance they'll win summary judgment. There's a 20% chance they'll lose a cross motion for summary judgment. and a 30% chance the judge is going to deny all and send it to trial. Okay? And at trial, the plaintiff thinks there's a 70% chance if they can just get to a jury, they'll win, and a 30% chance that they'll lose, but between now and trial, the end of trial, they're going to rack up $50,000 in litigation expenses. Okay? So, mathematically what we have is a compound lottery, where two of the outcomes are certain, summary judgment win, summary judgment lose, but the third outcome is itself a lottery in which there's a 70% chance of a win and a 30% chance of a loss, but with different outcomes there. So what we're trying to do here is essentially to value a compound lottery. And the first time I asked you, I was gentle and I said no risk aversion. So let's just figure out how we do this. Okay, so first of all, let's construct the trial, the sort of the second level lottery in our compound. And I'm going to make that an empirical distribution. There's a 70% chance we win $100,000, a 30% chance we get nothing, but we're going to subtract from that the $50,000 in litigation expenses. So that's my plaintiff trial lottery. And if we ever got to there, the mean of that distribution is $20,000. Okay? At summary judgment, we're going to represent the compound lottery as follows. We're going to say it's an empirical distribution with, and I know what I've done wrong. Okay. It's an empirical distribution where there's a 50% chance of winning summary judgment, a 20% chance of losing at summary judgment, and now I can say if I'm risk averse, if I'm risk neutral, I can just stick the mean in there. Okay? So I'm sticking the mean in there, and if I do that, we get $56,000. And so, as I sit at the summary judgment phase, the value of this case to me is $56,000 if I'm risk neutral. If the judge denies both motions and I have to go to trial, I actually just suffered a loss because I'm going to have to incur litigation expenses. And yeah, I'm likely to win at the end, but it's going to be an expensive win given that my hypothetical jurisdiction doesn't permit attorney fee shifting. Okay? All right, if we view this from the defendant's perspective, remember the defendant thinks it's a 50-50 situation at trial, and they've got the damages are liquidated, but their litigation expenses are more because they have snazzier attorneys who overbill the case. So, that's their situation, and if we take the mean of that, the case actually is worth $130,000. And so, if both parties were risk neutral, by the time if the judge were to deny both motions, there's actually a lot of room to settle this case. Yes?
The 130 is only the trial. You haven't done the summary.
Correct.
Okay.
I have not put it together yet, okay? So I'm saying, if the judge denies both motions for summary judgment, there's a lot of room to settle. The plaintiff values the case at that point at $20,000, and so the plaintiff should take it. It's rational for the plaintiff to take anything more than 20. The defendant values the case saying paying anything up to 130 is rational, and so there's room between $20,000 and $130,000 to settle the case. So if the mediator prides themselves on settling things, the mediator might hope that the judge denies both motions. Let's go to trial, and the case will actually settle at that point. If they're rational and both taking analytic methods for lawyers, and they all agree on this stuff. Okay. But we're not at trial yet. We're still sitting behind the veil where we don't know if summary judgment's going to occur. And so I'm going to construct my compound lottery here. Okay? And when I do that, where did I construct the plaintiff's lottery? Okay, so we need to do this. So let's do plaintiff SJ equals empirical distribution. Isn't it? Because I'm spelling empirical wrong, and when you do that, it doesn't know how to do command completion. And we'll just copy this part. Here we are. All I need to do is say what is the mean of plaintiff SJ. I did that already. Okay. So, pretend like the last 45 seconds never happened. So, sitting behind the veil where we don't know how summary judgment is going to be decided and the plaintiff is risk neutral, they're not willing to settle for anything less than $56,000. The defendant, sitting behind that same veil, is not willing to pay anything more than $53,000. Okay? And so, although it's close, this case is not rationally settlable by the mediator at this point in time. Now, if the mediator wants to, they could work over the plaintiff and say, how likely is it really that the judge is going to grant your summary judgment motion? I see problems with it. Don't you think there's a factual issue about this and that? And if we could just budge this number down to 0.45 and this number up to, say, 0.25, I bet we could settle this case. All right, so that would be one way of working it. But the other way of working it would be to count on risk aversion. So let me put a little thing here. And I am guilty of not doing this right. So let's do it together correctly. What we really have are now 4 possibilities. We have plaintiff wins at summary judgment. Plaintiff loses at summary judgment. Case goes to trial, plaintiff wins. Case goes to trial, plaintiff loses. And as we sit at the summary judgment phase, that's the lottery we're looking at. Okay? So let's look at what that looks like. We've got an empirical distribution, which one day I will learn to spell, in which the probabilities are 0.5, 0.2, but it's no longer 0.3 anymore. It's 0.3 times 0.7, the probability of winning at trial. And the next outcome is 0.3 times 0.3. That's the outcome. The judge denies both motions and you lose a trial. Okay, because they're independent events, so we multiply the probabilities. And what are the outcomes then? The outcomes are I win $100,000. I get 0. I win $100,000, but I have to pay $50,000 to my lawyer, or I get nothing and I have to pay $50,000 to my lawyer. Okay? So this is the plaintiff, I don't know, distribution 2. Okay? And if we took the mean of this distribution, it should be the same as it was before. Which it isn't. Zero 0.5, 0.2, 0.3. Let's look at how I wrote this down. 0.5, 0.2. Aha! Everyone see the little flaw?
Sure.
Right there. And it's always good when the numbers line up. All right. However, if the plaintiff has risk aversion, we can't just take the mean of it. Instead, what we need to do is our expected quantiles. And just like every other plaintiff, this is their weighting function, a 1.5 weighting function, meaning they take the worst of 1.5 draws. So let's calculate the expectation of the quantile of plaintiff distribution 2 with respect to Q, Q being distributed according to a beta distribution with parameters 1 and 1.5. And when we do that, we get $40,994. And so what's going on is the risk aversion has reduced the value that the plaintiff sees from this case from $56,000 to $40,995, because they're sitting there sweating that, oh my gosh, I could end up having to pay my lawyer $50,000 and get nothing. And that's now being weighted much more heavily in their mind than it was before. And because they're dwelling on that negative possibility, they are, in some sense, undervaluing the case. Okay? And by the way, this is why the market for litigation financing has started to materialize. You know how there's now people who are syndicating lawsuits and kickstartering lawsuits and doing all things that used to be illegal back in the day, and those may still be. But what they're doing is they are basically shifting the risk from people who are risk averse, plaintiffs with one case, to investors for whom, hey, this is one of 50 things they're investing in, they've diversified the risk away. And so you can now arbitrage the risk as plaintiff and sell your case and make some money, because the investors are basically saying this case is worth $56,000. They'll take an assignment of the claim. You're willing to sell it for anything over 41, and if that gap is big enough and transaction costs are small enough, you can make money by arbitraging the case. In the same way that risk transfer creates wealth in the insurance field, where you're taking a risk from someone who's fearing a loss, they're risk averse, and sending it over to an insurance company which can diversify that risk away and which is generally bigger, and so if they have to pay a $100,000 claim on somebody's house, who cares? Okay? Same thing. So it's actually a good thing to have markets in risk transfer, whether that be on the defendant side or on the plaintiff side, and yes, there are ethical issues and complicated issues about selling lawsuits, but we'll put those to the side. All right. From the defendant's perspective, what's going on? Well, from the defendant's perspective, we'll write defendant distribution 2. Okay, so what do they think? They think that there's this that's their 40% chance that the plaintiff's going to win at trial. So they're at $100,000. They thought that there was a 50% chance that their motion for summary judgment was going to prevail, in which case they're at 0. And there's that 10% chance that it's going to go to trial, in which case there's a 50% chance that they're going to win and a 50% chance that they're going to lose. And now if they lose, they're out $150,000.
No, at 180. His costs were more.
Yeah.
Oh, right. Thank you. And otherwise, if they win, they're only out $80,000. Okay, and so that's and so if the defendant were risk neutral, this should be the same number as we got before, of negative 53,000. And I'm breathing easy that it is. And someone tell me what to type now to calculate what our defendant's view of it is if they are risk averse, recalling that it just so happens that both parties act as if they use spectral measures and their weighting function is a PDF of a beta distribution parameters 1, 1.5. So, what should I type? Give you a hint. Starts with E. Expectation. All right, we're off to a great start. Next, starts with quantile of what?
Defendant's
What?
distribution deuce.
Of defendant distribution 2. Second argument being
Q.
Q. It could be
I
anything.
like X. So,
But
I
Q
used to
is
go
for
with X.
Q is for quant. That's what they should put in little. Right now, Q is for quail or something, right? In those alphabet books, Q is for quantile.
oh,
Kids
yeah.
hated that one.
You know what? There is a
You're
market
right.
in an alphabet book. Don't listen.
For
An
math.
alphabetical book
Yeah.
for analytic methods for lawyers. It'll probably sell more than my real book.
You need a picture though. Would you use like a box plot maybe or something?
Yes! This is the best idea I've had all semester. All right. We're on.
So many
Someone on.
distributions to use for the other letters too.
Yes.
One distribution.
B is for Bernoulli distribution.
Poisson.
What is Z for?
Z or C?
Z.
Z is for the Z statistic.
Oh yeah.
Okay, we can do it. All right, but getting back to business, how is Q distributed?
That was beta distribution 1, 1.5.
All right, and so the defendant thinks this lawsuit's worth negative $69,000, And so now there's room to settle the case somewhere between $53,000 and $69,482. And so mediators, one of their strategies so that they can say they solved the case, is to make both parties petrified of the worst case outcome, which they knew already, but now they know mathematically why that might be. And this, I believe, is all the stuff that is... Oh, what happens? That's right. The next question is, what happens if the case goes... The summary judgment motion is in fact denied, then how do parties value the case? And so then we're simply back to taking the expected quantile of the trial distribution for both sides. And actually at this point, the plaintiff is very scared of that negative $50,000 outcome, and our defendant is very scared of the negative $180,000 outcome. And so there's this huge amount of real estate in which the case can be settled, anywhere from $8,600 to $145,000, which in the real world might actually be a problem, because when there's this big a gap, there's so much more to fight over, and to try and get the best of it. But that's at least the math of it, is that in theory there's a lot more opportunity to settle. So that's how to do the homework in Mathematica. And I am going to post the answers in R so that we have enough time to look at networks, because I do want you to see them, because they're really kind of cool. So this is going to be a Mathematica day, because we're going to do networks in Mathematica. Save. And I will post that, what I just clomped down, and let's make R go away for now. Don't save that. All right, and let's close that. All right, so we'll close that. We'll close that. Don't save. And let's call up networks. Okay, so the UCC, right? You've seen it. How many of you are taking a secure transaction or payment systems class now? All right, so this is it's all gonna be clear now. What we're gonna do is we're gonna suck in the UCC, which is hosted on the Cornell site in various forms. The version that I'm sucking in may not be the exact current version because they fiddled with it, but for our purposes it doesn't make any difference. And I don't actually think it makes much difference anyway. All right, so I put it up on, and don't worry where this comes from. I sort of created this from Cornell, and that process I won't go through with you. So we import it. What does this actually look like? This looks like good old HTML markup, which at some point probably most of you have looked inside a website. And this is a fairly complicated thing. They've got all sorts of tags and the like, but that's what we're looking at. Okay? So our first task is to extract structure from this document. And there are a couple of ways in which you can think about the structure of the UCC. One is it has a formal structure. That is, there are articles which may have chapters, which may have sections, which may have subsections. And so the UCC is essentially a tree-structured entity, okay? In which each thing has more parts descending. But in addition to that formal structure, that doesn't actually capture the complexity of the UCC, because there are defined terms in the UCC which may be used in one subsection, which are also used in another subsection, or maybe even in another chapter. And so you could think about the UCC provisions being linked by those common defined terms, okay? Or by phrases that are used, or by internal cross-references that are used. So, as set forth in section 2209, the buyer may not rescind unless da-da-da-da-da, and that's set forth in section 2612 or something like that. So one of the things that we're trying, I'm just making up numbers, but anyway, what we might want to do is to create a UCC network, and there are lots of ways of defining what that network is. and then to use modern math to analyze it. So let me say a little bit about network analysis here, and back up. First, what do we mean by a network? And in its simplest way, a network means there are little vertices or nodes, and the vocabulary depends on which discipline you're coming at it from, and networks are sometimes called graphs. But anyway, there are vertices or nodes, and there are edges or arcs or links connecting them to other nodes.